For a long time, I've wanted to build a robotic arm, not just something that moves around, but something that can eventually move with real precision, closer to the kind of control you would expect from a serious machine. But before I can get anywhere near that, I need to understand the problems for myself. So I'm starting from scratch. The design, the 3D printed parts, the wiring, the code, the calibration, all of it. Because for me, the best way to understand a machine is to build the first rough version and see where it fails. What you're seeing here is that first version. It can move, it can hold a pen, and it is already trying to write and draw. It is far from perfect, but that is exactly why it is useful. But every test also shows the limits, the flex, the backlash, the calibration errors, and the difference between movement and precision. That is what this series is about. Taking this rough first arm and improving it step by step. So let me show you how it started. The first important part of this arm is the motors. Without them, nothing moves, and without controlled movement, there is no robot arm. For this first prototype, I'm using cheap 180-degree hobby servos from AliExpress. They are rated at around 11 kilogram centimeters at 6 volts, and they have partly metal gears. They are not industrial motors, and they are not perfect, but for a first test arm, they make sense. They are cheap, easy to control, and strong enough for me. But I don't want to use them completely blind. That is why I'm opening one of them here and soldering an extra wire onto the servo's internal board. And you may ask, why am I soldering a wire inside a servo? Glad you asked. Let's take one apart and look inside. Inside the servo, there is a small motor, a gear train, a control board, and a potentiometer. The small motor spins fast, but by itself it does not have the torque I need. So the servo uses all these gears to slow the motion down and increase the torque at the output shaft. Some of these gears are metal, but some are still plastic. That means if the arm gets stuck, or if the servo is forced too hard, the plastic gears can strip very easily. So this is strong enough for testing, but it is still a weak point in the design. The part I'm really interested in is this potentiometer. This is how the servo knows where it is. When the output shaft turns, the potentiometer turns with it, and the servo's internal controller uses that signal to know when it has reached the commanded position. What I'm doing is tapping into that signal. I'm soldering an extra wire to the potentiometer output, so the ESP32 can read the position too. The servo already has its own closed loop control inside. I'm not replacing that, I'm just exposing the position signal so my controller can also see where the joint actually is. Later this lets me compare what I told the motor to do with what the motor actually did. That is important for calibration, for finding the real limits, and eventually for recording and replaying movement. So this cheap servo becomes more than just a motor I send commands to, it becomes a joint that I can measure. Here I'm using a multimeter to test. The potentiometer has 3 legs. 2 of them are the ends of the resistor, and the middle leg is the moving contact, also called the wiper. When the shaft turns, the wiper moves, and the value changes. I connect one probe to the middle leg of the potentiometer, and the other probe to one of the outside legs. Then, when I turn the potentiometer with a screwdriver, you can see the resistance changing. That changing value is exactly what the servo uses internally to know where the output shaft is. So the extra wire I soldered is connected to that position signal. When the servo is powered, that signal becomes a voltage that changes with the servo position, and the ESP32 can read it with an analog input. Now I need to design the arm itself. For this first version, I wanted to keep the design simple and modular. In Fusion 360, I designed one basic arm link that I can print more than once. That way, if I want to add more joints later, I can reuse the same idea instead of redesigning everything from zero every time. The links are around 15 centimeters between the joint axes. That gives the arm a decent reach, but it also means the servos will have to work harder because the load is farther away from the motor. For now, I'm not lifting anything heavy. I only need the arm to move itself and hold a pen, so this should still be manageable for a first prototype. I did not use pulleys, belts, or any extra reduction mechanism in this version. These are already servo motors, so they already have gears inside. For the first test, I wanted to keep the joints direct and simple. The shaft design uses the same basic shape through the arm. I made 4 small keyways that fit into the moving shaft. The idea is that the keyways help transfer the rotation from the shaft into the printed arm link, so the joint does not just slip around the shaft. For the joints, I used skateboard bearing 608, which are 8 mm inside diameter, 22 mm outside diameter, and 7 mm wide. So in the printed housing, the bearing seat needs to fit the 22 mm outside diameter, and the shaft needs to fit the 8 mm inside diameter. For this test, I only printed 2 arm links. First, I remove the support material and clean up the prints so the parts can fit together properly. After that, I glue the small keyway pieces into the ends of the links. These keyways lock the printed link to the shaft. I mount the round servo horn onto the servo output shaft using the center screw that comes with the servo. Then I use small M2 screws to attach my 3D printed shaft adapter directly to that horn. This gives me a direct connection from the servo into the arm, so the torque goes through the joint with less play. I tighten everything carefully because any looseness here will show up later as backlash or lost motion. Even a small amount of play at the joint can become a much bigger error at the end of the arm. For the wiring, I crimp small DuPont-style connector pins. This makes it easier to plug the signal wires into the ESP32 GPIO pins, and I can move them around later if I need to change the pin layout. Some of the printed parts are still a little too tight, so I use a small grinding tool to clean up the fit around the motor housing. That is normal with 3D printed mechanical parts. The model can look perfect in Fusion 360, but after printing, the real parts usually need a little adjustment. To press the bearings in properly, I use a small bearing press tool. It is basically a threaded rod with handles and spacers, and it presses the bearing in evenly instead of forcing it in by hand. This tool is made for small bike bearings, but for this job it works perfectly. Once the bearings are in and the fit is cleaned up, I start assembling the joint and connecting the next link. This part is a little more tricky than it looks because the shaft has to line up with the small key pieces I glued into the other link. I have 4 of these little keys, and they all need to be aligned before I can slide the shaft through the housing, through the bearing, and into the other side of the joint. It works, but this is also where I realize the keyway idea needs to be improved in the next version. Gluing the keys in place makes the joint harder to assemble. A better design would be to use screws from the outside of the joint. That way I could lock the shaft in place after everything is aligned, and if I need to remove it or adjust it, I can just loosen the screws instead of fighting with glued parts. For this prototype, it is good enough to continue, but this is definitely one of the first things I would redesign. I use DuPont connectors for the 2 wires going to the ESP32, one for the servo control signal and one for the potentiometer feedback. For the power, I use Wago connectors to connect the servo power wires to the 6-volt output from my buck converter. This way, the motors get their power from the external supply, and the ESP32 only handles the control signal and the feedback reading. After that, I write a simple test program, upload it to the ESP32 and test the joint, and finally the arm starts moving. For a first mechanical test, I'm really happy with this. It is not precision movement yet, but the basic design works. The servo moves, the shaft transfers the motion, the bearings support the joint, and the arm moves without any major problem. This is it for part 1. In part 2, I will take this same idea and build the full arm. I will print the rest of the parts, assemble the whole robot arm, mount it properly, wire everything, and start testing the real movement. Thanks for watching. Don't forget to subscribe, and if you have any questions, suggestions, or just want to say hi, don't hesitate to leave a comment.